Hi everyone. I'm going to begin talking about the material in Chapter 4 and start thinking about the truth tree method. In Chapter 3, we defined all the semantic concepts of truth functional logic in terms of truth value assignments. So we considered the logical properties that were introduced in Chapter 1, and we firmed them up and thought about those in the context of SL and defined truth functional semantic properties. Then we saw that truth functional consistency can be defined in terms of truth value assignments, right? So that was our central notion, truth value assignment. And all the other semantic notions can be explicated in terms of truth functional consistency. That's what we did in that last lecture. That's what was done in section 3.6. We saw that all of the other truth functional properties can be explicated in terms of truth functional consistency. The method introduced in Chapter 4 relies on this fact. It relies on the fact that all of the semantic notions of truth functional logic can be defined in terms of truth functional consistency. I know that was, not the most riveting of lectures, but it was important for you to try to follow along with it because this is going to be pertinent to the work that we're going to be doing with the truth trees. Okay, so we've seen that we can use truth tables to test for all these semantic properties, but we've also seen that truth tables, however mechanical they are to construct, can be really cumbersome. They can get really big, and I've demonstrated inadvertently how easy it is to make mistakes when constructing them. They're not very elegant, even with all the shortcuts that we've developed. The tree method that we're going to look at now is less cumbersome than truth tables. And the rules for trees are based on the characteristic truth tables for the truth functional connectives, which we're going to start looking at those rules in this lecture. At this point, I'm assuming that everybody knows very well the characteristic truth tables for the truth functional connectives, because they're going to be important for understanding how we get the rules for the truth tree method. These trees that we're going to learn how to construct, give us a way of finding particular truth value assignments that make the members of a set of sentences of SL true. So the tree method is going to answer the question, is this set of sentences of SL truth functionally consistent? So given any set of sentences of SL, we apply the tree method to it, and it will tell us yes or no when we ask, is this set of sentences truth functionally consistent? Moreover, as I just said, they're actually going to give us, these trees are going to give us a way of finding truth value assignments that make a set of sentences true, if there is a truth value assignment that indeed makes the set of sentences true. And just remember that a set gamma, remember gamma is this meta variable that we use to range over sets of sentences of SL. A set gamma of sentences of SL is truth functionally consistent if and only if at least one truth value assignment makes all its members true. Okay? So the truth tree method will tell us whether or not a set of sentences is truth functionally consistent, and it will provide a way of finding the truth value assignments that do make the members of the set true if such truth value assignments exist. Okay, so remember, so the truth tree method is a test for consistency. Consistency is a property of sets. And that's what we became aware of, or we were thinking about in that last lecture of the previous module when we started putting set brackets around things. The reason for that is that consistency is only a property of sets. Truth, functional truth, falsity, indeterminacy, those are properties of sentences. Okay, so when we construct a tree for a sentence or a set of sentences of SL, we are, in a sense, going to be displaying the conditions under which a sentence is true. And to do this, we're going to rely directly on the truth table definitions of the connectives, the characteristic truth tables for the connectives. So I'm going to very quickly, do this quite quickly. I'm going to put up the characteristic truth tables for the connectives, okay? P, Q, we have P and Q, we have P or Q, P horseshoe Q, P if and only if Q, oops, sorry about that, P if and only if Q, and then we have negation. Okay, so let me see whether I can do this super quickly. True, true, false, false, true, false, true, false, true, false, false, false. I'll try to be neater. True, 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 false, true, false, true, 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 false, false, true, and then not P will be false, false, true, true. Okay, so those are the characteristic truth tables for the 5 connectives. So let's take a look at these. We see, for instance, in the case of the conjunction, there's just one way, so to speak, for a conjunction to be true, namely when both conjuncts are true, right? If we take a look at disjunction, and remember, the reason that I'm looking at the characteristic truth tables again is with an eye toward thinking about the truth conditions for sentences. Because remember, as I just said, when we construct a tree for a set of sentences in SL, we are in a sense displaying the conditions under which sentences are true. So I'm thinking in a slightly different way about how a truth value assignment can make a sentence of SL true. Okay, so for the disjunction, we see that there are 2 ways that a disjunction can be true, right? When one or the other of the disjuncts is true, or perhaps both. And even though there are 3 rows of the characteristic truth table on which the conditional is true, we can summarize those 3 cases into 2, because what we see is that whenever the antecedent of a conditional is false, or, and again I'm using or inclusively here, or the consequent is true, the conditional is true. So again, even though there are 3 rows of the truth table on which the conditional is true, we can summarize those 3 rows as 2. The antecedent is false, or the consequent is true, as in using or inclusively. Looking at the biconditional, there are 2 ways for the biconditional to be true: when both sentences are true, or when both sentences are false. Okay? Okay. So we're just thinking about these characteristic truth tables in a slightly different way. We can make similar observations about the negations of conjunctions, disjunctions, conditionals, and biconditionals. Okay, so I think the best way to get a sense of what's going on with the tree method is just to an example, and we'll sort of develop things along the way. Okay? So let's consider the set that has as members the sentences A and B, C, and not A or not B. Okay, so there's a set with 3 members. One's a conjunction, one's an atomic sentence, and one is a disjunction. And now I'm going to think about the conditions on which these 3 sentences might be true, sort of simultaneously. So I'm thinking, my background question is this a consistent set? Is there a truth-value assignment that makes all of these set members true? So the first thing I'm going to do is list these 3 sentences. I'm just going to write them down on a list. A and B, C, not A or not B. And now what I'm going to do, so the question is this truth functionally consistent? And now what I'm going to do is I'm going to think about the conditions under which each one of these is true. So going back to the good old characteristic truth tables, let's think about a conjunction, because the first sentence on this list is a conjunction of A and B. A conjunction is true when both conjuncts are true. So if there were a truth value assignment that makes the conjunction of A and B true, it would have to make A true and B true. So I'm just going to write those down in that list. Okay? So any truth value assignment that makes the first item in this list true is going to have to make A true and B true, because there's only one way that a truth value assignment can make a conjunction true, that is when it makes both conjuncts true. Okay. Taking a look at the next item in the list, it's just an atomic sentence C. Well, obviously, any truth value assignment that makes that sentence true is just going to make C true. So we're just going to leave that alone. There's one more sentence on this list, and that is the disjunction of not A and not B. So we have not A or not B. A disjunction is true, as we saw when we looked at the characteristic truth table for disjunction. It's true when one or the other or both of the disjuncts is true. So there are 2 ways, so to speak, in which the negation of A and the negation of B could be true, that third item on the list. And so we're going to branch this tree, right? There are 2 ways, and the ways in which we're going to represent the fact that there are 2 ways is by branching. And on one branch, we're going to write the first disjunct, and on the other branch, we're going to write the second disjunct. Okay? You're starting to see the metaphor, the tree metaphor, right? We got tree, branch, and so on. Okay. And now we have thought thoroughly about how a truth value assignment can make the first sentence true, the second sentence true, and the third sentence true. We know that, so what we're left with on these branches is, not A on the one hand and not B on the other hand. And we know that if a truth value assignment were to make not A true, it would have to make A false. And if it were to make not B true, it would have to make B false, right? So we've thought thoroughly about the truth conditions for these, the 3 original sentences. And now I'm going to look up the branches of these trees, because what we've got is the various ways in which a truth value assignment could make these 3 sentences true, if there were one that made all of them true, right? So on the left-hand branch, it tells us that, well, one possibility is that a truth value assignment makes, let me switch colors here, makes not A true, that is A false, and it makes B true. Oops, but it would have to make A true too, which couldn't possibly be, right? We couldn't possibly have a truth value assignment that made both A and its negation true. And so that attempt, what this branch on the left represents is, in a sense, an attempt to find a truth value assignment that makes our original set members true. And what it tells us is that it would have to make C true, A true, B true, and A false, but no truth value assignment could make A both true and false. And so that attempt to find a truth value assignment that does the job failed, and we represent that by putting an X on the bottom of that branch. Okay, so that branch is closed. We closed that branch because it did not succeed in giving us a truth value assignment that makes the set members true. So let's take a look at the right-hand branch. That says that, well, another way in which a truth value assignment could make, let me switch colors here, make the set members true is if it made not B true, that is B false, it would also have to make B true, which is impossible, right? So again, the right-hand branch represents another failed attempt to find a truth value assignment that makes the three members of the set true. And as we've seen, this little tree that we constructed here is really a thorough, exhaustive search for truth value assignments that make the set members true. Because we thought, well, there's only one way to make A and B true, that is, A would have to be true and B would have to be true. A truth value assignment that made A and B true would have to make A true and B true. And a truth value assignment that makes not A or not B true, well, it could make not A true, but wait a minute, that couldn't be because we already have A true. Or it could make not B true, but oops, that couldn't happen because we already have B being true. So all attempts to find a truth value assignment that makes the set members true failed. So this search failed. And what do we conclude from that? Well, what we conclude is the answer to our original question, is the set truth functionally consistent, is no. There isn't any truth value assignment that makes the set members true. We were unable to find one when we did this thorough and exhaustive search for one by thinking about the truth conditions for the members of the set. Okay? So when we construct a tree using the actual tree method, this was somewhat informal, what we're going to do is put a number. We're going to number the lines in our tree, the entries in our trees. So I'm going to do another example. If we followed, whoops, I got a kitty cat here. If we followed the tree method, we would have, numbered this 1, 2, 3, 4, 5. So this tree would have 6 lines. And another piece of terminology is when we thought about, say, the truth conditions for line number 1, which generated lines number 4 and 5, we're going to call that decomposing. See, more of the metaphor. We're decomposing, right? Trees decompose. Excuse me, Kate. We're decomposing the sentence, okay? So as we decompose a sentence, we're going to indicate that we've finished with it. We've finished thinking about it by putting a check next to it. Okay? Again, we're going to do a lot more examples. So again, when we looked at line number 3, which generated line number 6, we fully considered the truth conditions for line number 3. We decomposed it, and so we put a check next to it after we write down line number 6. And whenever we find along a branch that we've got an atomic sentence and its negation, we say the branch is closed, as I just said, and we put an X at the bottom of the branch. And once again, this indicates that that attempt to find a truth value assignment that made the set members true failed. Okay, so that's why we conclude from this little tree that the set is inconsistent because all attempts to find a truth value assignment that makes the set members true failed. They were unsuccessful. Okay, let's look at another example. In blue. We have A or B is the first member of the set. C or D is the second member of the set. not C is the third member of the set. And our question is, once again, oops, come back. What happened? Oops. Sorry, I pushed a button, it disappeared. Okay, and not C. And our question once again is this set truth functionally consistent? That is there at least one truth value assignment that makes the members of this set true? So, what we do is we list the members of the set, A or B, C or D, not C, and we number them. And then we're also going to have a column to the right of all of the entries in the tree where we indicate where we got those sentences. Now lines 1, 2, and 3 were set members, and so we write to the right, we're writing SM for set members, so we're indicating that those are set members. Okay? And now we're going to think about how a truth value assignment could make these set members true, and we're going to take them one by one. So I'm just going to start with line number 1, and I'm asking myself, if there were a truth value assignment that were to make A or B true, what would that truth value assignment have to do? Well, once again, we're looking at the characteristic truth table for the disjunction. It would have to make one or the other or both of the disjuncts true. And we indicate that by branching again. And so on line number 4, we're going to have on the left-hand branch the left disjunct, and on the right-hand branch the right disjunct. And we're going to check line number 1, indicating that we have decomposed it. We've thought thoroughly about what a truth value assignment would have to do to make that sentence true. Again, in this right-hand column, I'm going to indicate where that line number 4 came from. And line number 4 comes from the first rule that I'm going to write down, which is called disjunction decomposition. Let me write it down here. Disjunction decomposition, and I'm going to abbreviate it as that. So I have the disjunction sign, D for decomposition, and the disjunction decomposition rule tells us that if we have a sentence of the form P or Q, where P and Q could be atomic sentences or molecular sentences, these are metavariables, we decompose it by branching and putting P on the left and Q on the right. Okay, so that is a decomposition rule. That's the decomposition rule for disjunction. And so back to our little tree, in the right-hand column, I'm going to indicate that I got line number 4 from line number 1 by disjunction decomposition. Okay. Now, looking up these 2 branches that we've got here, we do not have an atomic and its negation, so these branches are not closed. These branches are both still open. So there's a lot of terminology that we're going to have to sort of pick up along the way. These branches are open at this point. They're open because we don't have an atomic sentence and its negation on it. These branches up here were closed, and we indicated that by putting an X, because on each branch we had an atomic and its negation, which of course no truth value assignment can make an atomic both true and false. Okay, so back to the tree. What do we do next? Well, line number 2 is also a disjunction, and so we're going to have to think about the truth conditions of that. Since both branches on line number 4 are open, when we think about what a truth value assignment would have to do to make line number 2 true, we're going to have to put the result of that under both of the open branches. So we know that the appropriate rule to apply to line number 2 is also disjunction decomposition. So we're going to have to put the results of applying disjunction decomposition to line number 2 under both of those open branches. So on line number 5, we're going to have C and D on those branches, and once again C and D on those branches. And we get that line from line number 2 by disjunction decomposition. Okay. Is there anything else to decompose? Well, line number 3, so we finished, right? The check indicates that we have dispensed with line number 1 and line number 2. Line number 3 remains. But line number 3 is the negation of an atomic. And there's no need to decompose that, to think further really about what a truth value assignment would have to do to make that true, because we know that a truth value assignment that makes not C true has to make C false. Another bit of terminology we call an atomic, or the negation of an atomic sentence. These are both called literals. So this tree, we have finished constructing this tree. In other words, the tree is completed. Another piece of terminology. The tree is completed because everything on that tree that is decomposable has been decomposed. Okay? So the only thing that on the branches that are not checked are literals. Okay, so this tree is completed. Let's see what we can learn from this tree. We're going to take a look at the branches. The left, so there are 4 branches here, right? The leftmost branch is going to, what each of these branches represents is an attempt to find a truth value assignment that makes the set members true. Each one represents kind of a search for a truth value assignment that makes the set members true. The leftmost branch tells us that, well, one possibility would be that a truth value assignment makes C true. It makes A true, but it would also have to make not C true, that is C false. So we have literals that conflict. We have an atomic sentence on line number 5 and the negation of that atomic on line number 3. So that branch closes and we put an X on the bottom indicating that it's closed. The only thing that indicates is that this was a failed search for a truth value assignment that does the job. But there are 3 other searches we need to look at. Let's take a look at them. And the next one over to the right, in a different color. The next one says that another possibility, okay, the first one failed. Let's see what this one does. Another possibility is that a truth value assignment makes D true, A true, and C false. That is not C true. Okay, that branch is open, and what the book suggests doing is putting a little O at the bottom of the branch indicating that it's open. Sometimes I do that, sometimes I don't. It doesn't really matter. It does matter that you put an X at the bottom of a closed branch, though. And so what I'm going to do over here on the right is I'm going to start collecting the truth value assignments that we get from, oops, I forgot about B, from the open branches. We have one open branch so far. So there are four atomics, A, B, C, and D. And this branch here that we just looked at in green tells us that a truth value assignment that makes D true, A true, and C false will make the 3 members of the set true. Note that it does not give us a truth value assignment for B, and I'll talk about that, the significance of that, in just a moment. Let's finish looking at the remaining 2 branches, okay? So the next one to the right tells us that, the branch that we just looked at, that was a successful search because it was an open branch. It gives us a truth value assignment that makes them true. But again, we'll come back to that in a moment. The next one over tells us, okay, another possibility is that a truth value assignment makes C true, B true, but would also have to make C false, which couldn't possibly be. We have an atomic in its negation, so that branch closes. And then finally, the rightmost branch tells us another possibility is that a truth value assignment makes D true, B true, and C false. Well, that didn't close. That branch is open. So every branch is either open or closed, right? It's open if there are not conflicting literals. There's no atomic in its negation. And it's closed if there are. So let's indicate what we found on the rightmost branch over in our little table here. So another possibility is it makes D true, B true, and C false. But again, neither A nor its negation shows up on that branch. Okay, so what we know off the bat is that this tree, I'm going to say, again, it's another little definition. This is an open tree. Why is it an open tree? Because it has at least one open branch. It's not closed. An open tree is one that's not closed. In other words, has at least one open branch. And in this case, we have two open branches. If we construct a tree for a set of sentences, and it has at least one open branch, that is, it has an open tree, then we know right off the bat that the answer to the question, is this truth functionally consistent, is yes, it's truth functionally consistent. Okay? But, as I said, what's kind of cool about these trees is not only does it give us an answer to the question, is the set truth functionally consistent, it actually gives us a way of finding the truth value assignments that do make the set members true if there are truth value assignments that make the set members true. And that's what I was doing over here when I was sort of collecting the information that we got from the open branches. So let's take a look at that again. So on the first, the green row, we had A being true, B being, C being false, and D being true, but neither B nor its negation shows up on this branch. This is the second one the second one in over the to the right. And so what this tells us is that B could be either true or false. So this branch, actually, the one in green, gives us two truth value assignments. B could be true, or all these other things happen and B could be false. So these two truth value assignments, the ones I have in green here, both come from that open branch, okay? Because it doesn't tell us about B, which means that B could be either true or false. It just tells us that any truth value assignment that makes D true, A true, and C false does the job, so B could be either true or false. And now if we take a look at the other open branch, neither A nor its negation shows up on that open branch. And I'm looking at this one, the one farthest to the right, the purple one. And so A could be either true or false, because what it tells us is that any truth value assignment that makes D true, B true, and C false will do the job. So A could be true or A could be false. So these two, the ones I've got in purple here, both come from this, the rightmost open branch. Note that we got the first and second, these two truth value assignments in this little list. These two, it's one truth value assignment, and we got it from both of the open branches. So we actually end up with, from this tree, we end up with this truth value assignment. Now I'm circling them in blue. This one, because the second one is the same, this one, and this one. We get three truth value assignments from those two open branches. But if our interest was merely in figuring out whether the set is truth functionally consistent, we know that it is because it has at least one open branch. But it's always a good idea, and I strongly urge you to do this, to, when you do a tree and it has an open branch, or it has more than one open branch, you should always collect the truth value assignments that you can from those open branches, because it gives you some interesting information. Moreover, it gives you a way to check to see whether you made a mistake in your tree, because you can go back and take really just a moment and plug those truth values in and see whether they do the job. So for instance, let's look at the first one that I've got in this table here, the one I've got in green, and let's see. So A is true and B is true. Yep, that makes that true. C is false, but D is true. Yep, that makes that true. And C is false, so not C is true, so it makes that true. And sure enough, it does. And I'm not going to take the time to do it for the other ones, but it's a really nice way of checking your work, like legitimately checking your work without, often when you're, you've been told your entire educational life, check your work. And I know that my own experience, like checking my work, when in math and so on, it just means like staring at it and looking at it again and proofreading it. And sometimes you just miss a mistake. But this is a genuine way of checking your work. You can actually collect these truth values, plug them back in, and see whether they do the job. If they don't do the job, then you know you goofed up somewhere along the line. You're not sure where, but you know that you should look for where you goofed up. So think about this, what we just did, this little tree, as opposed to a truth table that we would have constructed. If we had used the truth tree method rather than the truth table method rather than the truth tree method, we would have had to construct a truth table that has how many rows? We have A, B, C, and D. It's going to have 16 rows. That's going to be kind of an icky truth table to construct. I mean, initially truth tables were fun to construct, but nobody wants to construct a 16-row truth table. This was a much more elegant way of answering the question, and much easier. There's one more comment I want to make about this tree. I'm kind of milking these two trees over this tree. When I constructed this tree, and now I'm going to, it's unfortunately going to have to go to a different, scroll down a little bit. I'm just going to rewrite the original set here. When we constructed that tree, we didn't think at all about the order in which we decomposed the sentences, right? We just did them 1, 2, 3. Okay. Sometimes thinking strategically is appropriate. And in this case, it doesn't shorten our work significantly, but it's a nice example of how your work can be shortened if you do think strategically. So let me set up the tree once again. And we have A or B. Remember, we just list the set members, C or D, not C. We indicate that they are set members by putting SM over to the right. And now what we did in our original tree is first we decomposed line number 1, then we decomposed line number 2. We ended up with 5 rows in our truth table. But if we had decomposed line number 2 first, look what would have happened, or look what will happen now that I'm going to do it. On line number 4, I'm going to apply good old disjunction decomposition to line number 2, and I get C on the left and D on the right. I check it, indicating that it's decomposed. I've sort of dispensed with it. And then on the right, I indicate that I got it from line number 2 by disjunction decomposition. Okay? Look what happens. Already we have a branch that closed. We have C and not C on that left-hand branch, and it closes. So the advantage to decomposing line number 2 before line number 1 is that we got a branch to close right off the bat. And that's going to be a nice strategy for us to sort of have in our toolbox, so to speak. So, if decomposing a sentence will get a branch to close, then go ahead and decompose that first. The order in which you decompose these sentences doesn't make any difference at all in the outcome, in the answer that you're going to get, or the truth value assignments you're going to be able to retrieve from open branches, because what we're doing is, if we decompose everything that's decomposable, we're it's going to be an exhaustive and complete search for truth value assignments, regardless of the order in which we decompose stuff. Okay, so now let's go ahead and decompose line number 1. Line number 4 on the right is open, so the result of decomposing line number 1 is going to go under D, and that's going to branch, and we have A and B. Okay, and we indicate that we got line number 5 from line number 1 by disjunction decomposition. Okay, and now I'm going to look up those two branches to see whether the branches are open or closed, because now everything that's decomposable in this tree has been decomposed. Everything is either checked or is a literal. Remember, a literal is an atomic or the negation of an atomic sentence. Okay, so this next branch we have A, D, and not C. So that's open, right? We do not have an atomic in its negation. And then on the last one we have B, D, and not C. And so we don't have we don't have an atomic in its negation there. And we're going to get precisely the same truth value assignments that we got when we decomposed it, just by doing it in the order in which the sentences appeared. Okay, again, not significant. I mean, the original tree is a little bit wider. You know, it didn't shorten our work significantly, but using this strategy in the future of, you know, if there is a way to close a branch by decomposing a sentence, decompose that sentence, that could shorten our work significantly if our tree were more complex than the one that we're looking at right now. And so again, we could collect the truth value assignments, and we're going to get precisely the same ones. We get in the one that in red, we get A is true, D is true, C is false. So why did I put A there? That was silly of me. That's a thinking writing issue. True. And so B could be either true or false, right? We get two truth values from that. And then the one that I've got in blue, B is true, D is true, C is false. And so A could be either true or false. So we get exactly the same truth value assignments, not surprisingly, that we got up here when we didn't think strategically. Okay. One more thing I want to say before I end this lecture is we wrote down this decomposition rule sort of in so that we could use it when we construct trees. There is a decomposition rule that we used in our initial tree. Remember up here when we decomposed A and B, we said that a conjunction is true when both conjuncts are true. So we were implicitly applying conjunction decomposition to line number 1. And so let me just write down that rule. Conjunction decomposition tells us that if we encounter a conjunction on our tree, we decompose it by listing the two conjuncts because, and again, this comes directly from the characteristic truth table for the conjunction, right? There's only one way that a conjunction is true, that is when both conjuncts are true. So that's the rule for conjunction, and the one for disjunction is P or Q. We have P, Q, and we check these when we decompose them. I'll leave you with the question, how many decomposition rules do you think we're going to end up with? We have 2 so far, right? We have one for conjunction, we have one for disjunction. There are 5 truth functional connectives. One of them doesn't require any decomposition because if you've got the negation of I take that back. It does require decomposition if P is a molecular sentence. So I'll just, okay, forget I said that. I'll come back, if it's the negation of an atomic, obviously it doesn't require decomposition. But thinking about this, there are five, and negation is significant for this, there are five truth functional connectives. How many decomposition rules do you think we're going to end up with? Hint, it's more than five. Why would that be? And some of you might be thinking, oh man, I've already learned all of the characteristic truth tables for these connectives. Now I'm going to have to learn all these rules. Yeah, you're going to have to learn them, but it's not a matter of memorization. You already kind of know them because you already know the meanings of these connectives, that is the characteristic truth tables for the connectives. So, and again, the decomposition rules come directly from an understanding of the meanings of these connectives, the characteristic truth tables for the connectives. So, think about that question, and we will answer it in the next lecture. Okay, I'm going to stop here. You're going to like trees. You're going to they're less work. They're more fun than truth tables. And bye for now.